solved. So we're going to start 3.3. We are learning exponential logarithmic functions not just for fun, but actually because many models in real life, biology, medicine, and engineering, and business have exponential growth. That's what we call exponential growth models. If you see exponential function, you need to know how to work with it, and that's where the logarithm starts, and so on. In the population or if the population or quantity is increasing exponentially, that's what you saw in some movies. They say, oh, the zombie apocalypse, the cases increase exponentially. Yeah, that means fast. And it also means that the rate looks like this formula. We can describe the population by the model P, usually P is population, of T is time, equals P sub 0, that is called initial population, which means how many people, rabbits, bacteria we had at the time equals 0. So say one bacteria and it's dividing, or only 2 people, 2 rabbits, and now we have 55. So what happened? And so on. P is a population at any time t, positive. K, so it's times e raised to the kt. K is the growth rate, and T is time in days, months, weeks. If you talk about planets, years. If you talk about the division and spread of bacteria, microseconds. So T depends on what you're talking about. Growth not necessary. If K is negative, it actually can be decay. Decay with key, yeah? Okay, you got growth or decay. You will see different examples. So we need to learn to work with these models, and these are very popular, very popular. That's definitely something everyone around the world is learning. P equals P sub 0 e to the kt. See actually that at 0, P at 0, if you plug 0, you will get P sub 0 times e to the 0 times k. So at time 0, minutes, seconds, how many things did we have? In my table, it's like 10,000 bacteria right now. That's going to be my initial population. In this class, we have 70 people. That's going to be initial population. E to the 0 is 1, so it's just P0. That's exactly the definition of the initial population. At 0, it is P sub 0. And usually we do not start from 0. Because if something is growing exponentially, it should have an original moment to start with. Now I'm gonna, yes, no? Let me know. Okay. Question for you, people smart in this class. All of you are smart, so I'm kind of curious to ask this question. I always ask it. Exponential function looks like this. We already know that. It's a very fast growing thing up to infinity, and it's like shrinks to 0 on the left. In the population models in real life, it starts from here, so it doesn't have negative side. If we claim that population grows, we say if population is growing, increasing exponentially, and for you to know human population is growing exponentially, I don't know, my fish in the tank is growing exponentially. Why my fish in a tank then does not over-occupy the whole fish tank if it's growing exponentially? Exponentially means grows to infinity, right? Why? What do you think? Resources. This is exactly what the thing is saying. A real life, so exponential growth mathematically looks like this on the left side. But logistically, I actually did not know this word. Logistically means real life. In real life, it starts growing exponentially, but instead keep growing to infinity. There's some kind of carrying capacity. How did you call it? What did you say?
I lost the
See, I forgot too. So interesting. How would you call it?
carrying capacity?
Or resources. Yeah, that's what I want to say.
Sorry, I wasn't sure.
There is some kind of restricted resources, space, food. There are competitors around you. They start restricting your growth, and your graph of the function slowly bends, becomes concave down. Look at it. It was concave up over here. There's some point of inflection happens. And this point of inflection is when resources start being not available to everyone anymore. And that is why Petri dish, bacteria in the Petri dish, they blow up exponentially, but then slowly start decreasing the rate. So they will still divide, but they will be slower rate. Why? Because bacteria or cells, they talk to each other. And it's interesting that in our body, it was interesting mathematical problem actually, why one hand is not longer than another hand. Surprisingly, when our body grows, our brain knows what symmetry is and says when you're a child how the bones are growing, it does know where to stop, how to stop. That is the limits of your capacity of your body. And it stops at the same time, which is also pretty phenomenal. So the idea is there's not infinitely many space and food, then the exponential growth will slowly bend into concave down shape and will still keep growing, but slows down. Because cells talking to each other who reach the end of the petri dish, they keep giving the signal behind, please stop dividing so fast. There is no space here anymore. And then that's how the communication happens. So it's very interesting. This is a famous coronavirus cases. It is exponentially growing. So it would be interesting. I usually show epidemics graphs before COVID. It was very interesting. Now kind of everyone saw that. So it's not that interesting anymore. And as you can see, data points are points. And then you fill in the gaps, just like in childhood, we draw the line through the points, and it gives us exponential growth. So then this one is pretty cool. I like this one. This, you just collect the data, but it looks exponential, you see? So people can make agreement that it is exponential growth, and they build a model. And that's how do they build the model? Knowing the formula. This is one more explanation. You don't have to copy this one, but this is pretty cool. Look at that. So survivors density on the left has a color coding, and then death density exponentially people are dying over here. The percentage of death cases are here. Infected density is keep increasing. Bless you. Infected percentage, uninfected is going down. Infected is going up and dying. Pretty cool idea. So as you can see, it's exponentially growing at the beginning, and then it starts bending and becomes concave down at some point. Pretty cool. So you can watch this animation at home. Right? And then let's do the example. Do you have any questions or you want to add something about this? Because that's actually a pretty cool idea. In general, exponential growth, anything you can imagine, from frogs to molecules to birds, cows, humans also spread exponentially. Cancer cells. So cancer cells are the one that stop talking to each other. I think I mentioned this before. The mutation happens in the genetics. Cancer cells cannot tell back anymore. There's no space anymore. Tumor, please stop growing. There's no space in this human to grow and eat. And they either cannot hear, so the hearing gene is broken, or they cannot speak, so the speaking gene is broken. And that's why they keep growing, and that's why there can be cases when there is a human with a huge tumor on their head and they're dying. It's not very smart for inhibitor to kill its own host, right? Because this living from that host. And that is caused by the mutation that they stop talking to each other, these cells. So that's a pretty cool idea here. So suppose we have $25,000 is invested in a saving account that earns 1% annual interest compounded continuously. The amount in the account 2 years later will be following this formula. So we're going to do biology examples. This is the investment example. And it's nice for you to know what it means, because you all need to be doing investment at some point. So as you can see, there are lots of exponential functions as well in the business. That's why when we teach business calculus, they know that they need to learn how to work with exponential functions, differentiate them, integrate them, solve equations. And we're going to do solving today, right now. So A is the amount in the account at any time t. Is 25,000. Why? Because when you start it at zero time, it will be 25,000. E raised to the 0, so it is 25,000 after all. That is what we call P sub 0. In this case, we can call A sub 0 since it's investment. Some people call it I sub 0, but it is initial value. So we started with something. In order for investment to keep accumulating, you need to start with something. You're investing into a saving account, and it has 1%. Where do you see this 1% in the formula, by the way? Do you see it somewhere? 0, 0, 1. Thank you. This is our k, exactly. So a sub 0, it's our p. This is p sub 0. And then k, let's go back to the formula and see what k was. K was over here. So t is a variable, k is a constant. That is constant. That's why it's called a continuous growth rate, but it's constant. While t is a variable here, it's my input. So k is attached to t. What number is attached to t? 0.01. That makes sense. K is 1%, but we don't use percentages in our models. We use decimals. 0.01. That is my growth rate. Again, if it's negative, it's a decay rate. So let's answer a couple questions to see that you understand the situation here. Question Q1. What is the account's value after 1 year? Find the account's value after 1 year. After 1 year. Answer. Right? It's like Q and A. It's like a very English thing to say. Answer. So how would you answer? What should we plug in? You should be careful and go and read what T is. T can be minutes. T can be years from 2005, and then you have to add up to whatever it is. In this case, it's actually a very simple case. T is just years later. So what is going to be my equation? I'll put it in green. Any ideas? A of 1. 25,000 e to the 0.01 times 1. Good job. So I'm taking my t and plugging it into the exponential function. And that's why we learn how to work with exponential functions. You grab your calculator, write down e raised to the 0.01, multiply by 25,000. What is your expectation? Is it going to be a number higher than your initial investment, lower, or the same? Higher.
Wait.
How do you know? Why?
Wait. I've got a question.
Yes?
That doesn't figure out right because he. Oh wait, never mind.
Chris is going to get it. You will see right now.
Because e to the 0.0 would be the 100 to the b, right?
E to the... Huh?
I'm trying to think what e to the 0.01 would be.
No, you can
That
just...
would be the 100 root of b.
Okay, let's see.
Sorry, I got it. I was thinking.
Why not? Let's check. That's a good question. What is e to the 0.01? E to the 0 is 1, but adding even a little bit more than 0 increases exponential function to 1.01. So e to the 0 is 1, but you see even a little bit more. That's why 1% sounds like nothing, but it makes a difference. 1%.
I was thinking of, I made a mistake here to give negative powers or
Yes, that's what I thought too. Yeah.
Either one would be
Negative. Negative will have a fraction, right? Here it is. Now it's supposed to be 1. Chris, look at the screen. It's supposed to be 1, but now it's a little bit less than 1 because it's negative.
I just made a mistake.
Right? So no, very good question. Good job. So you said it should be a little bit higher. How do you know? 25. 2. Who knows why the number grew? Yes, anyone? No, I mean, what is your kind of intuition behind it? What did we just do? 25, 25, 1. Too many 25s.
Yeah,
1.
Wrong.
And then one more 25 over here.
All right, find me the back offers that.
How do we, yeah?
It's because we're earning it.
Yeah, we're earning money. We put 25,000. It says 1% will be adding. For how do we going to be adding? Not plus 1%, but exponentially. That means you put this and you let it rest in the saving account. This will be adding a little bit, couple more every year. We're checking what's happening in 1 year. In 1 year, From 25,000, we end up to be at 25,251 plus something. So it's $251 more than we used to have. Now you know approximately how it grows. It's not a linear growth. It means next year it's not going to be again 251. You have to recalculate it again at 2, at 3, and so on. That's why it's interesting. Question 2. Question 2. How long will it take for investor to double? That's a good question. So you know that you want to buy a house, for example, in the future, right? How long, but you know the price of the house, 50 grand, 50,000, right? How long will it take for this initial amount to double? To double. Question mark. And that's the thing, you already know how much you need. You need $50,000, but you don't need how long. You don't know how long it will take you to wait to get this money. Maybe it's going to be in 3 years. So you're like, yeah, 3 years, let me finish this job application, and you'll be all set to buy a house. Maybe it's in the months, maybe it's in 100 years. So we need to figure out, does it even make sense to wait for this amount or not? That's a good question. What do you think we don't know here? So we have only input, output, and K. Look at this model carefully, just a second. A is my output. It's dollars. A are in dollars. T is my input. It's in years. K is 0.01 in percentages. 25,000 is initial amount in dollars. Which one we don't know this time? T. Last time we did not know A. They gave us T equals 1. This time we don't know T, but they gave us A. What is my A? 50,000, right? It's going to be answer. $50,000 equals original amount, $25,000. E raised to the 0, 1, T. And we are solve for T. Does it make sense? Or any kind, it doesn't have to be doubled. Maybe I want specific amount, like $3,000, $35,000, $55 for some reason. So I can put it on the left-hand side as a known future amount. On the right-hand side, it will be initial amount times exponential growth, 1%. 1% can also change at some time. But T is my time. We need to solve for T. To dig out this T from exponential function, we're going to be using the ideas I taught you last time, how to solve exponential equations. And this is the problem on the quiz right now. So it's nice if you pay attention. How to dig out the exponent from the exponential function. You use logarithmic functions. Here's the steps. This is what we call exponential equation. EQN is equation. Exponential equation. In your quiz today, you will be asked to solve exponential or logarithmic equation. Step 1, isolate the unknown part. Isolate. If it's log, isolate log. If it's logarithmic equation. If it's E, isolate E. 0.01 T equals. Isolate means have this whole E or log and an equal sign. How should we do that? Let's just divide by 25,000. Dividing by 25 gives me 2, right? That's exactly this double thing just happened. So very interesting that we just divided by 25,000. I guess your notes will not be confusing if I leave it like this. So let me write down 0, 0, 0, which is 2. So now we have E 0.01 T equals 2. That's a very pure exponential equation. Exponential function on one side, numbers on the other side. Step 2, to get rid of exponential equation, or specifically to dig into the exponent, we're going to apply inverse function to get rid of exponential function, which is log. You can apply log of any base you want, but with E, it makes sense to use ln. I will apply ln to both sides. You can also use definition if you want. Apply ln to both. Don't forget both sides though. Both sides. There's a whole theorem that says you can do it because logarithmic function is continuous. So now you will have ln e to the 0.01t. People usually skip this step because we all remember that ln of e is what? Ln of e is 1. So this piece is 1, right? But then this piece will stay. Properties of exponential function says, of logarithm actually, this exponent can go down. One way of seeing it. One way of seeing it is 0.01t is multiplied by ln e, which is 1. Or the other way of seeing it is ln undoes e, the exponential part will stay. So that's my input. Two ways of seeing it. So 0.01t equals ln t. Solve for the unknown. T equals divide by 0.01. It will be ln 2 over 0.01. Which is actually multiplying by how much? 100, right? So it's 100 ln 2. Dividing by decimals means multiplying because it's 100ths. Right? So it's 1 over 100, you flip the fraction.
Doesn't it do something when you multiply a logarithm like that?
No. Logarithm inside multiplied, yes, but logarithm outside is not.
I thought I could convert that to something else.
And if you calculate this, so what is this number? You give it to manager in your office and they're like, so what is this number? How many years should I wait? Who knows?
69.
69.
3147.
Oh, it's even 3 months? Okay. 0.3 years. 69 years to double the amount? That's why 1% sucks. And that's why when you invest, you hope to find a better percent, okay? So it's interesting, I asked my friends in Ukraine how much percent do we have. They told me 14%. I'm like, wow, we can go all reach in 14%. They said, yes, but the problem is inflation. Today, hryvnia can be 1 to 25 to dollar. Tomorrow, it can double 50 to 1. And whatever you earned will die tomorrow because of the inflation. I'm like, oh, okay, so it's very good percent, but it's very not stable. In America, it's very stable, but very small percent because of that. So that's always a connection between economy. Economy here is stable, and that's why it's 1%, but it's all the time. Ukraine has a very jumping currency, so it's a huge percentage, but it's not reliable at all. So you're going to do this problem right now in the quiz for you to know how to solve the equation. Let's answer more how long to double. So 69 years, too long. That's kind of not very smart. Now, how fast is the amount growing after 10 years? Yeah, that's a good one. Last question. Question 3. Oh, that was question 2. Question 2 we did. Question 3. So put this in the box, 69.3 years. Now see the keyword. Hopefully you will see the keyword. How fast? Wait, what is that? Derivative. So keyword should tell you how fast. That is already something we learn in calculus class. Again, logarithmic function, exponential functions are taught in high schools actually. So if you never seen it in your high school, it's just because your high school did not teach it. But in general, we teach it in high school. That is not nothing new. That is not anything new. But the how fast part, that is calculus part. How fast the amount growing. How fast the amount growing after 10 years. After 10 years. And you're like, oh, isn't we just plugging in a of 110? We just did the same thing. We plugged 1, so what is the difference? Why this question is different? It's a derivative. So compare with the first question. The first question was, find the account's value after 1 year, or what is happening in 1 year? The third question says how fast the amount is growing. Growing means changing. This is rate of change. Change or how fast or rate is a keyword for derivative. Speed is derivative, first derivative. Acceleration is second one. So all of this should give you a hint that we are looking for a prime at 10, question mark. And that is why we're teaching you how to differentiate exponential logarithmic functions. Fun? Yeah, it's super fun. Where is your excitement? Let's differentiate. Let's see if we can do that. There is extra credit on the quiz for differentiation. So I don't remember what A is. Let me write down again. 25000 e to the 001t, right? Let's differentiate that. A prime is, who wants to try? Chris.
No, not
Well, interesting part, literally the same, because remember the anecdote, e to the x gives you e to the x. So I agree on that. This number stays because it's attached to exponential function. So derivative gives you the same thing. Derivative of exponential is still exponential. That's what the joke says. If you missed the class, you don't know what the joke is. Times, what is the part?
0.01.
The derivative of the function in the exponent. That's chain rule. Chain rule says you did good, but there's a function in the exponent, which is a linear function, 0.01t. Derivative of that is 0.01. So this is my derivative. You can simplify it if you want. It will be 250. So we're dividing by 100. 250 e to the 0.01t. That is my a prime at t. At any time, this is my speed of the investment. So now I can see the speed. Let's plug 10. Then a prime at 10 is 250 e to the 0.01 times 10 years. 10 years. That is simplified into the 250 e to the 0.1. That is a number, approximately, anyone got? $27629. What are the units? They should be per, remember? If it's rate, it should not be a finite number of dollars. It should be dollars per, what? Years. Because we differentiated dollars. So A was in dollars, derivative was dollars with respect to time t. So dollars per years, per time. This is the growth at that particular year. Like I told you, in 1 year we got something like $250, but it's not going to be the same as second year or third year or fourth year. Specifically, in 10 years, we can say that the amount is growing differently every year. Is growing not linearly, not like, hey, I will give you 250 per year. No, it's keep increasing every year. It's growing by $276.29. And you see I have a European habit to put dollars at the end. Only Americans put dollars at the beginning, actually. So everyone else will put it at the end because that's how you're saying it. $276.29 per year. Per year. After, that's important. At what kind of moment in time? 10 years. I can write down years. 10 years. And that is a difference between A of 10 and A prime of 10. What is the change versus exact number? Questions? What do you think? This will be a fun chapter, to be honest. You'll read lots of applications. Biological, medical, injections have exponential decay. Definitely growth of the population. What's population of the city, Tempe, and how it's growing exponentially. You can predict how many people you'll have in 10 years, but also what is a change in 10 years. Yes?
Is it 276.29 on average per year?
No, it's actually not the average. The average would be dividing by the 10. It's kind of different formula there. This one is more specific, like that year.
So
Very good question, yeah.
on the 10th year,
Yeah. Graphically, you will see it like so. We can graph the function right now. And then it will be, so plot. We have A equals 25000 e raised to the 0.01 t. This is too many zeros, yeah? Yes. Oh, no, it's fine. No. 0.0 and then e. Let's do it this way. So this is the graph. You're not very smart. Okay, let's do t like so. Parentheses matter, as you can see. This is the exponential function. Years are at the bottom, so 100 is too many. We checked 10. 10 was this. Let me do this anew. Oops. Oh, I don't need this.